Hi, everybody. This is lesson 4. I'm Alyssa Pierce.
I'm Faith Bratton.
I'm Heather McPherson.
And I'm Chelsea Schlottman. Hey, Faith, what is the reflection of any given figure?
Okay, the reflection of any given figure is basically when a line is reflected over another line and it makes like a flip over the line of symmetry, which is given as our yellow figure with the two figures on the left side. We use a reflection model in question 1 when we were explaining the motion between Devontae and his friend, using with the given picture to the left whenever he rotated it when he was supposed to do a reflection. There's different types of reflections. As you can see, there's a translation, rotation, dilation, and reflection. Also, there's another image to your right, which is showing a line of reflection when it's just rotating over a line and it's the exact same figure. Hey, Alyssa, what is an example of a rotation using pattern blocks, and could you rotate more than one way?
Well, when working with rotations, you have to know what they are first. So a rotation occurs when you move an object around a point or origin clockwise or even counterclockwise. So in this example I've shown you, you can see a clear rotation that occurred in the midpoint, which we call the orange square. So in this particular problem, the shape has actually gone clockwise, but it could have gone counterclockwise if you were looking at the figure on the left. Hey, Heather, why is this figure not a vertex figure?
So first off, we need to know what a vertex figure is. And to explain it, the total surface area must equal 360 degrees. So with this figure, you have 3 different shapes, and they have 3 different surface areas. The first one being 135 degrees, 108 degrees, and 120 degrees. If you add all 3 of these together, you're going to end up with 363 degrees, which is not equal to 360, so it would not be a vertex figure. Hey, Chelsea, when rotating a figure, what would a 180-degree rotation look like?
All right, so we're going to start off with this figure here. And we first, if you think of a circle, you think of 360 degrees. So we're going to take this particular shape, and I've drawn this line here so you can kind of understand what the line of symmetry is. We're going to circle this shape around in a rotation, and that square is going to stay in the same exact position. So a circle, as I said before, is 360 degrees. So for 180, that's half of 360. So we're only going to rotate this figure on the left halfway around the circle. So if you rotate it halfway, you see that the triangle is flipped to the bottom, and then the trapezoid is on the top. Hey, Faith, how many lines of symmetry can one figure have?
Okay, so a line of symmetry is when you reflect or flip a figure over a line and the figure appears unchanged when the figure has a reflection symmetry or a line symmetry. Okay, these are some figures that we're going to demonstrate to see if they have lines of symmetry or not, or how many they have. Okay, for this first one, we have a triangle. This triangle has 3 lines of symmetry. As you can see, it has 1, 2, and 3. The next figure we have is a square. Okay, this one has 5 lines of symmetry, or 4. Okay, as you can see, the different ones. And the next one is a circle. The circle has infinity lines of symmetry, means that it can be folded, rotated any kind of way, and no matter which way you fold it or rotate it, it will have a line of symmetry. So there's endless amounts. Hey, Alyssa, of the 2 shapes on the screen, which one has lines of symmetry, and how many lines of symmetry does it have?
So here we have 2 shapes. One kind of looks like a stair shape, or like I like to call it, it looks like something from Tetris. And the other one is a rectangle. So when you have a line of symmetry, it must be able to be folded down on itself and not have any gapping or overlapping of any kind, no matter where it's moved. So obviously, if we were to fold this Tetris shape in half, vertically or horizontally, it would not meet perfectly. It would overlap and gap in certain areas. But if we look at the rectangle, we can see that there's 2 clear lines of symmetry, one vertically and one horizontally. So the rectangle has 2 lines of symmetry. Hey, Heather, how are these triangles congruent?
Okay, so when looking at these triangles, you have triangle QPV and you have triangle SPV. So in order to tell if they're congruent, you're going to look at them. They're two right triangles, and lines PQ and lines PS are going to be identical to each other. Here's your points again, PQ, PS. So the lines are going to be congruent. They're equal to each other along with the angles that are within it. So you'd have a side angle side property, so it makes it congruent. Hey, Chelsea, what is a line of symmetry, and can you explain how it's used?
I guess the first off, a line of symmetry is sort of like a mirror image. So if we flip the image over the line of symmetry, or the straight line that we have, if we flip the image, half of the image over that line, it's going to look the exact same. So we're going to start off with the shape here, the heart. If you put a line right down the center of it, that is automatically counted as a line of symmetry. It has one line of symmetry. You can fold the left side over the right and it stays the exact same, or you could fold the right side over the left and it also stays the same. And then we also have a circle. And as stated before, a circle has an infinity number of lines of symmetry, so you can make as many lines through it as you want, and it's going to stay the same no matter how you flip it. Hey, Faith, what is rotational symmetry?
Okay, rotational symmetry is when a shape still looks the same after it's been rotated a few times. It can be rotated by any angle between 0 degrees and 360 degrees. For example, a regular hexagon, as seen on your left, has rotational symmetry. As you can see in this figure, it's been rotated a whole bunch of times, and it still looks the exact same no matter how many times it's rotated, 360 degrees or more. Okay, the figure on your right is a triangle. Okay, with it being rotated one time, as you can see, it does not have rotational symmetry with it being rotated and it making a whole different object looking reflection. Hey, Alyssa, can one shape have multiple symmetries?
So one shape can absolutely have more than one symmetry. So an example I'm going to show you today is this diamond-like shape. So starting with the obvious fact that the diamond shape has two lines of symmetry. So if we were to divide this vertically or horizontally, it would fold over on itself perfectly, therefore giving it that line of reflection or line of symmetry. And it also has rotational symmetry, which is what you just spoke about. If we were to turn this 90 degrees, it would look like it's laying on its side. But if we were to turn this 180 degrees, it would superimpose on itself and become the same diamond shape it was before. Hey, Heather, so the girl is about a quarter mile from the cliff. How far away is she?
That's a good question, Alyssa. So when looking at the diagram, first you need to know exactly how far it is for a mile. And so your mile is going to be 5,280 feet. Knowing that, and we're trying to look for the quarter mile, you're going to divide it by 4. And you're going to end up with the quarter mile equals 1,320 feet. Chelsea, can you show us what rotational symmetry is?
Of course. So we're going to start with this diamond shape or rhombus. And if we, as Alyssa had said before, you can rotate it 90 degrees and it looks like it's over on its side. So it's not going to be the same as it was before. And in rotational symmetry, we want the figure we start out with, when we flip it, we want it to look the exact same as the original one. So this first one here, we only rotated it 90 degrees and it's on its side. And then over here on the far right, we're going to rotate it another 90 degrees to be 180 degrees. And it's going to look the exact same as the original. So this is rotational symmetry. Hey, Faith, how do you find the vertex of a figure?
You're muted, Faith.
Thank you. Okay, so back to what we were saying. Okay, a vertex, we're just going to give the definition at first. It's where two corners or a plane where lines meet in an object. Each line is called a vertex, or if there's more than one, it's vertices. To find the vertex, we need to find the center, which would be like the center where all the vertices meet, which would be 360 degrees. When we were given with this problem in our homework, we knew that each figure was different. The red was 335 degrees, the blue was 120, and the green was 108. We knew when we added these up, they were 363 degrees, but that's not an equal vertex because it needs to be 360. So we added the 3-degree gap in to take away the 3% extra of the 363 to make it 360. So then we knew that this would be a complete vertex. Hey, Alyssa, what is a vertex figure?
Deja vu, right?
I know.
All right. So a vertex figure, going a little bit more in depth, is actually defined as any arrangement of non-overlapping polygonal tiles that surround a common vertex. So like you showed in the previous figure, it has to be 360 degrees. So in our homework, Myra had an issue and she thought that this was 360 degrees, but as you just explained, it was 363 degrees. So by adding that 3-degree gap, she would have a vertex figure, but without it, her figure was absolutely not a vertex figure. And so that's what that is. Hey, Heather, how do you find the height of the cliff?
So in our homework, we were given a lot of information on this problem, but the equation that you're going to use is height of the cliff divided by the quarter mile, which again is 1,320 feet, and it's going to equal 1.5 inches over 2 feet. You can't have inches and feet, so you're going to change everything into feet. So then you'll have height of the cliff by itself on the left side. It's going to equal 0.125 feet times 1,320 feet divided by 2 feet. So you'll have the height of the cliff is going to be approximately 83 feet once you round it. And Chelsea, are any of these triangles congruent?
All right, so first we're going to start off with the figure on the left. And first we need to kind of understand what congruent means. It basically just means if you were to flip it over, it's going to be the exact same as the figure on the other side. So to know if it's congruent, we just need to know if it's the same as the shape on the other side. So for the first figure on the left, we have QPT highlighted in the yellow over here. And then we have SPT. Those two are going to be congruent to one another because they are the same. Sorry about that. Then we're going to look at the second figure over here on the right. We have QPV, and then we also have SPV. Those two are the same. And I have it highlighted here in kind of a rainbow color to highlight the actual triangle figure. If you were to flip that over, it would be the exact same triangle as SPV. So those two are congruent. And then also on the second figure, if you look at the bottom portion, we see that SVT is going to be the same as QVT. Because again, if you were to flip that over onto the QVT, it would be the exact same. So they are congruent to one another. Oh, sorry about that. Losing control of my mouse. Hey, Faith, what is a transformation?
A transformation, okay, there are many ways to explain a transformation. And there's the different points of a shape, line, or point. There are two different types of transformations. There's rigid formations, which does not change the shape or the size of the pre-image, or there's a non-rigid transformation, which does change the size or shape. The different types of transformation are given in this, as we explained in the first slide of mine, was the translation, rotation, dilation, and reflection. Translation is just kind of sliding the image over where it's the exact same. Rotation is rotating the shape in 160 degrees, 180, 90 degrees. Dilation is making the object smaller, and a reflection is reflecting it over a line of symmetry. Hey, Alyssa, what is a size transformation?
So size transformation is another word for dilation, which you kind of touched base on. So both are defined as a shape that expands or contracts but holds its shape and orientation. So, for example, if we have triangle ABC and we shrank it down like the second figure right here, it still held its shape and its orientation, but as we can see, it's obviously one is big and one is small. And we can see this in everyday life, the way that we see Starbucks coffee cups. Those cups are actually a dilation of each other. We have the tall, the venti, the grande. No matter what you get, you're getting the same cup, only a different volume. Next slide.
wasn't going there.
Hey, Heather, is angle QVP a right angle?
That's a good question. When you look at this triangle, you see that the triangle QPV is actually a right triangle. And so that's kind of, you can see that with the square to show that it is a right angle. And then you have your other triangle that is connected to it. So it is a right angle strictly because that other triangle and the QPV have to be, they're supplementary to one another. So angle V is supplementary to the other angle V, which means it's going to equal 180 degrees, and a right angle equals 90. So Chelsea, what does it mean if a shape dilates?
Alrighty. So we have already talked about this tonight, so I'm just going to kind of touch base on it a little bit more. So on a plane, if we have a particular shape, and here I have a right triangle, dilation just simply means it's going to either grow in size or shrink. So you're going to have the same exact shape, but it's either going to grow or get smaller. And in this example here, I made the shape get larger. And as you can see, it's the same right triangle that we started out with, but it got larger as it moved up the plane. Hey, Faith, do these figures have a line of symmetry or rational symmetry?
On mute again. Okay. With this first figure, we're showing half a circle. We'll ask ourselves, does this figure have a line of symmetry? Okay, yes, it does have one line of symmetry, as you can see right down the middle. But does it have rotational symmetry? No, this figure does not have rotational symmetry because when it is rotated, it looks like a half moon. It is not the same figure as it once was, so no, it does not have rotational symmetry. But this rectangle on the other side, does it have lines of symmetry? Yes. It has 4 lines of symmetry, as you can see given. That's 4. Okay, but does this one have rotational symmetry? Yes, it does, because when this figure is rotated, it is still a square or rectangle. Hey, Alyssa, can you show how to use tiling when working with these lines of symmetry, lines of reflection?
Sure can. Tiling is a great tool for visual learners like myself. Math used to not be my friend until I learned about these little guys. So in our lesson from this week, Ephraim and Devontae tried to use tiling to demonstrate a line of reflection, but actually ended up showing us rotation. So when trying to solve this type of problem, I always like the visible way. So here all we've done is we've drawn that line of reflection through that orange square, and we've kind of flipped it. And you can tell it's a line of reflection because if you pay attention to those triangles, they're still facing that same direction, that right direction. And whereas if you rotated it, one set was facing right and one set was facing left, so we knew that wasn't a clear reflection. Hey, Heather, what are some transformations?
Okay, so we've already hit on this a couple of times, so I just want to go over and just make sure you understand a little bit more. One type of transformation is translation. The shape stays the same size. It doesn't change. You go up the same amount of times. You go over the same amount of times. So again, just don't change the shape and you'll have a translation transformation. The next one is a rotational transformation. And that's just rotating it. In my example, I rotated it off of a point, a specific point, but it doesn't have to be rotated off of a point. It could be rotated by itself. The next one is going to be a reflective transformation. You'll have a line of symmetry, and you just reflect that shape over that line of symmetry. And then the last one is a dilation transformation. In my example, I have a small figure that is the original, and I dilated it, I made it bigger, so it would be a dilation transformation. Chelsea, can you show us an example of something that does not have rotational symmetry?
Sure can. So we're going to start out with the triangle. And if you remember, rotational symmetry just means if you were to rotate that figure a certain degree, then it would look the exact same as it had previously looked before you rotated it. So with this triangle, I'm going to rotate it. And when we rotate it the 180 degrees, it does not look the same as it had before. So this one does not have rotational symmetry. And then we're going to look at the trapezoid here. And if I were to reflect it 180 degrees, or rotate it, I'm sorry, 180 degrees, you can see that it also does not look the same as it had previously looked before the rotation. So if it has rotation, it's going to look the same whenever you do rotate it, and if it does not, it will not look the same. And that's it for Chapter 11, Lesson 4. I hope that, guys, helped you get a better understanding. Thank you.
Thank you.